let's probably get started. Yeah.
Okay, I think I will start and let others then join whenever they are.
Sure. Yeah.
Okay, now let me just go where I was last time. Does anyone have any question from the previous lecture when I started bearing and bypass interaction? Any clarification you need?
Sir, actually, I had a doubt.
Yeah.
When there are more than thousands of fasteners in all the structures, is it possible to do this bypass and bearing means interaction verification for all the fasteners, or typically some other different design philosophy is followed?
Well, these days the process is computerized. So what happens? Each fastener we will develop the load from, because finite element models they generate the load, say. So for every fastener, you will pick up the load, decide about the bypass based on the procedure. In fact, it's a bit involved procedure. Then you write down the procedure, everything put in the Excel spreadsheet or whatever software you can develop, and just run everything. That's very convenient then. Otherwise, you will be struggling to find which hole is critical, which is not. And the reason why we want the margin for every place or every element is that we want to have an idea that if some damage occurs somewhere, earlier probably the margin was higher, but with the damage margin go down. So when you have to analyze the damages, you would be interested in knowing the original margins for the structure, what was the margin. And that is why that we analyze every element of the structure, and there's a margin summary written down for every element, every fasteners, like every place in the structure. So it is not only analyzing critical margins, but whole of the structure, a summary sheet will be there with every place of the structure, the margins will be there because they are needed. So,
Sir,
yeah.
Sir, but what was told was, sir, you told like it is dependent on the direction of loading also. So at each location it will be different. So does this procedure account for various possible loading conditions and all?
Oh yes, various load cases are analyzed. So what happens? There are thousands of load cases in the aircraft structure which are analyzed. Then there's a load sorting when you are analyzing. So finally you will consider, okay, there may be only 5 or 6 critical load cases out of thousands load cases. It's a big process. Load sorting itself is a big process in the company because you have to consider every load case, and then depending upon, okay, which part may be critical for which load case, some may be torsional critical, some may be bending critical, so you have to assess everything together. So it's a big process to really pinpoint which are the load cases which are critical. And then after you have sorted out, maybe there may be a dozen cases or 10 cases or 5 cases critical, then what happens? Then you will analyze the margins for all those load cases. And there would be summary sheet created. Okay, some margin maybe for one load case may be lower, another load case may be higher, but another place, another margin may be lower. And that is why it's very important to consider all the critical load cases. And it's a big process in the aircraft industry. We don't leave any load case which is critical. So again, if you're analyzing joints, suppose the flap, and there are 500 fasteners, suppose, spars, ribs. So there will be summary sheet created on Excel report that all the fasteners will be analyzed, and you just click the button and it will give you the margin for that fastener. So, and these days, what happens with earlier when the high-end calculations were done 50, 60 years back, that was a different story. But today, it takes no time. Whether you analyze 100 or whether you analyze 1,000 in Excel spreadsheet, and those Excel spreadsheets connected to the next strand basically, directly. So output, you get converted to Excel and it churns out a lot of margins. Laminate analysis is done on Excel spreadsheet finally, holes. So it depends upon how you interact the softwares. There's a lot of choice available now. So Boeing has developed internal softwares which are linked, and then automatically you generate all the margins.
So this load sharing also is automatically picked from the analysis, right, sir?
Well, load share is done. Sometimes load share is normally done by FEM will always do that. But normally what happens sometimes the fittings, when we are looking at some effect of various parameters, we may do individually by hand, two-dimensional analysis or one-dimensional analysis. So that is more critical for the fitting. Otherwise, most of the things, load share capability will be taken care of by FEM. It will show the loads. There we don't have to do any load share. Automatically it will do the finite element. And even in the fitting area, it will be done. But what happens sometimes, the modeling becomes complex. So sometimes every effect is not modeled in that. And we can then resort to the fitting individually. The load sharing may be done by some programs which Boeing has two-dimensional and one-dimensional. So there are many procedures depending upon the situation and how your modeling is done.
Okay, sir. Okay.
So it's a case by case. We have to decide. But I can understand load share when you want to do for all the holes in the spars, ribs, by hand, it's very difficult. So just FEM will churn out. And sometimes you get a lot of surprises. FEM is showing, and that's where the trick comes. FEM sometimes gives surprises. Stress concentrations. It predicts very high load. Then we are investigating. Oh, this is very high load. Then what happens? Why it is so high? And suddenly next element, there is a significant drop, which may not really happen in practice. That is another thing. Sometimes you get surprises. So it's a very highly interactive process. It is not you just accept everything from the finite element. We have to really then interrogate it. Looking into the research.
How we validate that, sir?
Pardon?
No, in that case, how we validate those FEM results? Like as you told now, if it is prone to error.
That is looking into the physics of the problem. So sometimes what happens, then you look into the element, whether the element type is not properly behaving. So you have to really then consider your physics, why the behavior is erratic, the result from FEM. And as during my lecture on certification, I did discuss that the validation of FEM analysis method by a full component test. And I showed one graph where we had to compare the strains, the test strain to the FEM strain predictions. And they have to be matched within plus minus 5% according to FAA regulation to validate the model. And as I said that time, that first model which we had, and before testing, we found when we got the test results, some of the results were out by more than 10%. So again, our engineers had to work why there is a difference. Looking into the stiffness, the ply thickness or laminate thickness, looking into the type of the elements. And that took a lot of time. And especially for the buckling, nonlinear analysis. I didn't show the chart where the buckling characteristics had to be shown, because what happens, that is even more difficult to really predict the onset of buckling from the test and matching it with the FEM. That took us several months to really validate the post-buckling behavior, compare the results of such a large structure with a FEM. That was not a simple match. So the modeling takes quite a bit of time, and then comparison and validate it with the FEM results, the test results. So again, there's no simple answer to clarify how do you check it or how do you validate whether those stress concentrations which you're seeing is reasonable or non-reasonable. You have to consider physics, that whether it looks reasonable or not.
Okay, sir.
So in fact, quite often we had the results from FAM like a spar or RIPS, where the stresses came out to be very high for the radius, and we had to increase the weight of those spars or the ribs. And physically we were feeling that somehow the results should not be that high. But again, then we have to trust. If we cannot justify, then we have to trust the model result.
Okay, sir. Okay.
And this is what happens. So sometimes, in fact, I've seen in the industry that just to validate a small part of the structure, because you are getting some funny result, it may take quite a bit of time. Because unless you can justify, you have to accept what you get, high stresses. Then it goes like a, one element is showing very high or next element is showing very low. The stress gradient. Somehow FEM is showing a stress gradient. Really, we feel it should not exist so much. Suddenly stresses can't drop so much. But again, then we consider some kind of averaging process. So again, what I'm saying, the bottom line is you have to really look into the physics. You cannot blindly accept what FEM churns out. So when there is a doubt, you then discuss it, consider the hand calculation, try to look into all the parameters, and then accept the results or reject it. Does it make it
Fine.
give some idea? Okay. Any other question?
Yes.
Okay, now I started discussing the bearing bypass interaction.
Radhaswamy, did you have a question?
No, sir.
Okay.
Okay, so in fact, I have added a couple of slides here, but that's just to clarify. I'll send a revised presentation later on. I had discussed, this tension side, bearing and bypass interaction, how we get it. So essentially, the procedure was in order to determine this line, which is showing bearing and bypass interaction. This is bearing, and this is bypass strain. And we showed, okay, at this high stress concentration point where, this diagram, okay, here. So where I showed there's a bearing and then there's a bypass, and at this point, you have the stress due to the bearing, and at this point also due to bypass, and total stress will cause the failure. So this is what our objective was when we are trying to determine that line which I'm showing. It is a summation of the bypass and bearing stress. And the way we went ahead, we wrote the expression sigma maximum equal to sigma max 1, 2. Then here this is bearing and this is bypass. And we considered KB, the bearing stress cushion factor, to be 1, and KT will be determined based on the stiffness. Okay, now, so I wrote this, that's equal, this is equation is, because I said, okay, what happens when you have a bearing and bypass stresses together at sigma max, then failure would occur when the stress reaches FTU. And then from this one, we wrote this equation. So we got finally the equation for bearing bypass in tension mode. And this is what finally I wrote this equation. The derivation is given over there. And then we have to write the compression one. Okay. So in compression, we consider, okay, this is bearing only, and then there's a bypass in compression. So total is this scenario where there's a bearing and the total load. So at this point, there's an interaction, high stress will exist. So the way I'm considering for the compression, I've explained the situation over here, that there's a bearing here and bearing here. Then this bearing stress is causing some damage over here due to bearing stress, as you can see. And in bypass also, there's a fastener. Fastener is supporting the load. Unlike in tension, the fastener acts, it doesn't do anything. But in compression, the fastener supports the load. And that is why what I've done here, if you see the free body diagram, just taking a section of this one. So P bypass, and we are considering, okay, fastener is just providing a total support. And the average stress is FC then at this section. So it's behaving like a continuous section, and we are ignoring the effect of the whole. Just the fastener. Fastener tries to take up the load and transfer it to this section. So we consider, okay, this continuous section. And that is why I have just written here FC equal to P bypass upon WT, the totalist. And then, and the philosophy over there is, when we are using this one, I've tried to explain here, the fastener sharing load in the compression. So compression bypass only at low stress, no hole damage. When the hole damage is not there, of course, this can be considered like a failed hole, and the fastener is supporting the load. However, at high stress, what happens during bearing, there's a hole damage occurring. And then the effectiveness of the fastener in supporting the load is reduced. And then this section may behave like an open hole compression. And this is what we will show in the compression bearing bypass interaction. We make use of the compression, open hole compression, and filled hole compression. So we are saying here, fastener losing contact, fastener not able to provide any load path. The advantage of load relief is lost when hole damage due to bearing occurs, and the hole thus behaves like an open hole. And that is what I've considered over here when I'm trying to derive the bearing bypass interaction for the compression. You have a PT, that is a total load, bypass, bearing load. So stress at point B, and that's where the failure occurs. In the case of tension, we said the failure would occur over here in tension load. In compression, this will be the failure point. So F total over here is equal to FBRG, the bearing stress plus the compressive stress due to bypass. So bearing stress at point B could be expressed as KBRG, this KBRG into PBRG upon DT, and KBRG could be greater than 2, but we'll consider it 1. So therefore, the total stress is equal to PBRG upon DT and PBR, and we'll convert this in terms of strain. So this is total stress, and the failure would occur when this stress reaches the bearing stress allowable. That's what I've used the equality for the failure. So that means I convert this in terms of strain. So E bypass plus I divide by E. So E bypass plus FBRG upon E equal to FBRG upon E. So this is what we have done in the compression, the interaction diagram. I'm just going a bit faster, you can interrupt me, but the things are clear over here. It's equation derivation mainly. So now what we are saying, that E bypass, that equation is there, it will be interacting with FBRG over here, and here, this will keep on going up, and interact somewhere. But we are saying, okay, it can't exceed EFHC, that's our limiting value, and EOHC. So this is open hole compression strain reliable, and this is filled hole compression reliable. So this is the line which we derived from here, this equation. So we are saying here, okay, our interaction equation will be E bypass equal to minimum of EFHC, this one, and E bypass minimum of, but what happens, we do not consider this. So our design criteria, I should just envelope it, that design criteria will be this one. We do not consider the filled hole compression as our interaction diagram chart. It is just to get this line and showing over here, in fact, so our criteria is compression bearing stress interaction based on Nelson, okay. So US, okay. But our limiting value is this one. The reason why we don't consider filled hole compression, because at high stresses, the hole may get damaged and it will then behave like an open hole. And so the advantage of fastener will be lost. And so you don't want to jeopardize the safety of the structure by being optimistic. So our design criteria is always that we consider the open hole compression as the cutoff value. Okay. So in totality, this is tension we explained, and this is a compression chart. So our envelope is this one. Compression and tension. Okay, now this was based on a single fastener, and we considered some assumption for the bearing a stress constant factor. However, this is not that reliable. In fact, in order to improve the situation of this, there's a recommendation in Mill Handbook 17 also you'll find, and the STM 2 fasteners or 3 fasteners bearing test is used, because this is just using 1 point over here, 1 point over here for this line. But in actual situation, it's better to get some more points. So the best is, because there are some methods which are based on 3 fasteners also, but 3 fasteners is not convenient because the load distribution is uneven. Generally, to get some middle point, to get a better interaction chart, a 2 fasteners test data is also taken. So it's basically a bearing coupon, which I'm showing here, where 2 fasteners are there. So we'll get a point in the middle of that line for tension. Compression does not change. It's the tension only. And based on this test, we'll develop another point. So I've shown here in this one. So this is the test. Now what happens in this one when you are testing in 2 fasteners? You are getting the bearing, you are getting a bypass also here automatically. In single fastener, you don't get that. And I won't go into the details of this. This is just a test data here. So based on the test data, you get EDFS, that is failure strain for double fastener is equal to E bypass is equal to P upon this. and F by G that is allowable for two fasteners test, bearing test is equal to this one. So these are, so it's all explained here. I won't go into the details. So what happens when you have the two fastener data, you are getting this point from the test, you get another this point from test. So what happens then? You know this point from En, that is the lower of open hole tension and filled hole tension. So this point is known. This point is known from two fasteners. This point is known from two fasteners test. So 1, 2. These 2 points are known. And then you draw this straight line, which intersects over here. In the design, we know this point from our single fastener test. So that means we cannot have bearing stress allowable more than this one. So we just project it vertically up. So our interaction chart is this, essentially. Now this should be similar, not exactly same as we had determined for the single fastener test. Single fastener test, we got only this at this point, and from open hole compression, so tension, filled hole tension, we got this point. And then we were trying to use that theory in order to achieve this line. Now that equation is simply coming from the test data based on two fasteners. This line equation comes from this data point, which is based on two fasteners test. Okay, I've written down the equation, and this is what it is now. I won't go into the details of this, and then to plot the design, I've just considered, okay, based on this typical to design value, we'll factor it and determine this line. And this is all explained in my list write-up, how to generate bearing bypass interaction. And rather than having a single fastener, this is based on the two fasteners test as recommended by Mill Handbook 17 and also ASTM. And rest of the things are explained in this equation. I won't go into the details. So finally, this is the equation here based on two fasteners test. Okay, so I've just written down over here some process for interaction values that two fasteners test with same parameters, but with various 0% is fiber laminate. Say this coupon test data provide FBR, GDFS, which I've explained, and the values for notch tension test come from 6.4 millimeter hole. The bearing stress allowable up to single fastener shear coupons, and the compression is already discussed previously. So finally, this is the diagram, interaction diagram. Now, the things are explained over here, and I'll send this revised lecture notes tonight after the talk. You can go through this one, and if there are any questions, if it is not explanatory, you can ask a question next time. So if there are no questions now, I can leave this interaction diagram and move further. Any question anybody has on interaction diagram? I mean, you can read this later on and of course, and just digest the method. Okay. Okay, I've just written some comments about the interaction charts. In preceding slides, the bearing bypass interaction charts are shown for the bearing bypass loads aligned in the same direction. Okay. this case. Now, life is not so simple. In actual structures, you would have the multi-axial loading. So the bearing load will not be always in the same direction as your other load, bypass loads. So this is case 2, this is case 3. That means you have to generate the interaction diagrams considering these cases. Now, I have not considered the interaction diagrams for these cases over here. But I provided a reference by John Hartsmith, and this you can download from Google. This is available free, and you can read. I think I might have sent this publication, but however, anyway, if you don't have it, you can download it, this IGARD CP. So John Hartsmith has discussed how to develop the interaction in the case of shear and the biaxial loading. The reason why I have not done it because it would be unnecessarily complicating more like, here. So I just wanted to keep it simple to give you the idea of the importance of the bearing bypass interactions for the analysis of the joints. Okay. Now, if you remember last time I said there are two methods which are normally used in this slide, which I showed. This one, where I said bearing bypass analysis when you are do by bearing bypass interaction charts or point test loaded hole. And I said the interaction charts do have the limitation because you have to prepare the interaction charts for loading scenario, various parameters, geometric parameters, the laminate parameters. It makes the determination of all those data quite complex, but that can be done, But the point test based method does not need all those interaction charts based on lots of test data and interpreting the charts. This is far more simpler and requires much less test data and very versatile. There is no limit. Any type of loading scenario you can consider. And that is why this is much better to follow. So I'll just provide some guidance to that. As I can't derive the equations, they are not easy to derive, but I've given the reference here. So now this method, point test method, is based on this reference. Again, the same Air Force, this report, which I had sent last week, or this can be downloaded. Actually, it's available free. This work was done by McDonnell Douglas, or now Boeing, of course. So it's reliable. Now, Ivanovsky and Garbo, they developed a theory using a complex variable method, whereby they considered a generalized loading scenario. Suppose this is a generalized loading scenario of a plate with a hole. The load is being applied on it. And so you want to analyze this generalized loaded structure for bearing and bypass. Okay, so the procedure is by using a point stress criteria, and I did explain last time a bit of it, but let me just explain a bit more. So you have a plate with a hole, the bearing load over here, and there's a bypass, the total load, and this is a bypass, sorry. So this scenario, that means all this load being applied over here in addition to the bypass load, of course. Then you have the stress I explained last time, so stress distribution. So the criteria, point stress criteria is that at some characteristic dimension, this stress value is equivalent to the unnostalgiable value, strain or stress, then that will be the failure point. So in terms of stress equilibrium, so sigma y, or we call it strain, at x equal to r plus d naught, r is the radius, plus d naught is the characteristic dimension, at y equals 0 is approaching sigma naught, which is unnotched stress allowable, or EY, that is a strain, is equal to E naught. E naught is a strain allowable for this condition. Okay, E naught failure gross strain for the eliminated load direction, and this is, I've just explained what, and D naught is a characteristic dimension. Okay, now point stress method remarks. So point stress method depends on correct determination of the characteristic dimension D naught for the laminate. The characteristic distance depends on loading mode, tension, compression, bending, laminate layup, hole size, plate width, edge distance, countersink, environment, percentage, fibers, and load direction. So again, the D naught is not constant. It's dependent upon many parameters which I have listed over here. So what happens here when you're trying to determine, okay, D naught for various loading scenarios, laminates. So we will test a few combinations of these parameters, and that is done for the open hole tension compressions, filled hole tension compressions. So based on that, we'll determine the characteristic dimensions, D naught, and use those characteristic dimensions when we are trying to determine the failure at this point, because what happens, I'll explain it later on. In the complex loading, of course, the point of failure point may be this one or this one or this one, this one, this one, anywhere. And that's what we'll have to consider. So now, in point stress method remarks, it is assumed the characteristic distances under multi-action loading are same as determined using uniaxial loading. However, characteristic distances may vary depending upon loading type, material types, which I've explained. So to determine characteristic distance for each failure mode and fiber directions, you carry out some tests and determine these dimensions. When Ogonowski, they considered in their analysis, they considered a single characteristic dimension without varying at all along various points on this circle. But later on, of course, the methods were very modified to include the variations of characteristic dimension depending upon the loading modes. And that, of course, involves a bit more calculations, but these days, you have the softwares and they will take care of all those variations and just develop some equations, expressions, put them in your program, and all the variations will be considered. Okay, so the method, I won't go into the details again. I'm just explaining how Garbo and Ogonosky developed the method. So this is a problem of interest. We have a load, and this is one element where I have shown the loads. So this is equivalent to this bypass plus bearing. And now to solve this problem, what they did, they used complex variable method in order to determine the stress field due to this load, all these loads, stress field around hole at any point within the laminate. If it's only unidirectional, of course, the simple solutions are available. But when you have multi-action loading, you have to consider some method so that, because the simple equations are not available. So they use a complex variable method. So once they developed the stress due to this multi-action loading, and then they developed the equations for loaded holes and superpose that loaded holes, unloaded, and then they determine the stress at a point. So now the method is, if you want to read the details of the method, look into this report, which I said can be downloaded, or you have, I think already I provided. So method applicable only to in-plane loadings, NX and Y and XY, and the bearing load. It assumes constant corrective dimension distance in this method, according to this one. But later on, modifications have occurred. So define the geometric parameters, define corrective dimension, define ply stress and strain reliables, using the analysis method for loaded hole, determine the ply stress at corrective dimension at an angle. So what happens here? The equations, as I said, quite complex. They're not easy to put them. I have not put it, but what the method I'm explaining, based on these equations, and again, the equations you have to put in software. There's a software available, BGFM, which use those equations and churns out the results. It's not simple. So in order to understand the procedure, okay, procedure I've said, for point stress, you want to evaluate at a point stress, the stress or the strains based on the method. And once you evaluated that, compare strains with reliable. So what happens here, you go along the corrective dimension, all along this circle, and the variation could be at 2.5 degree or 5 degree. Calculate the margins, and then lowest margin will be your margin, because in multi-action loading, you don't know whether the failure will occur from here or here or here, here. That's why for every ply, the analysis will be done at various angles, find the minimum margin, and so you write the minimum margin. Now, so in a joint, somebody asked half an hour back, if you have 1,000 fasteners, yes, this analysis will be done for 1,000 fasteners. But it takes no time these days. All those, that analysis may take only about a minute. Okay. I've written here to define ply stress criteria. It could be psi, L, psi, or any other failure criteria. but normally our preference is to use maximum strain criteria for failure. I won't go to the details of this anyway. Strain criteria for margin calculations I've just typically shown, which you probably, those of you have done the laminate analysis may appreciate it. So what happens to the analysis, you may have a bending strain and the mid-ply strain. So suppose the bending plus mid-ply strain, so total strain here is higher than over here. So normally when we are doing the analysis, we will analyze the strain in 0 degree direction, strain in 45 ply direction, strain in 90 degree direction for each ply, and strain in minus 45 direction, because the strain could be higher in this direction or this direction, this direction, this direction for fiber. So we calculate the fiber strains in each direction and then determine the minimum margin. So maximum strain criteria is used. For margin calculation, in current analysis, bending and plane strain allowables are considered equal, and thus margin can be calculated as normally they will be different. Bending with strain allowable is slightly higher than in plane strain allowable, but this is a conservative method over here. So MS fiber tension S1T upon E1T. So this is allowable tension strain, and this is applied tension strain minus 1. Same thing, compression. Okay, so that's how you calculate the margins for each ply. Okay, next one is bolt strength. Okay, anybody has question on this?
Sir, whatever you told now is basically when the bolt is under shear. So is this the same applicable when the bolt is under tensile load, like out of plane load? Basically,
well, out of plane load, then there won't be any this bearing.
Exactly, sir. That's what I was thinking. So in that case, how it is?
Well, then the different mode of failure I would be explaining now. Different failure modes. This, like say.
Okay, sir. Okay, fine. Okay, sir. Then in that case, you please continue, sir.
Okay. So bolt strength analysis. Now, the other modes of failures which I consider. So here, bolt tension, bolt shear, bolt pull through the laminate, bolt shear tension interaction, and bolt bending. So far we consider, okay, the laminate, the bearing failure. When the shear load is there, that's what it is. You don't design the joints, you don't want to have autoplane loads, but you may have some small autoplane loads, which you have to consider so the failure doesn't occur by pull through. Because all the joints you want to design is for the shear. Okay, now some of the failure modes I have highlighted over here. For fastener tension load, so you have the tension load up, and suppose I've just shown say laminate being the tension load being reacted by some reaction over here. Fastener with tension force be applied, and it laminate with supported diameter D3. So that means free body diagram would be here when you are trying to pull it up, the reaction load on the head, and say the support load I have shown over here. So it creates some bending at this section. Okay. Again, this is from free body diagram. I don't have to explain everything over here. So now, looking at this fastener load and the stresses. Now what happens due to this one? So you are pulling this, the stress due to the reaction may cause the fracture over here, or it can fail over here, depending on the load and type of fastener, countersink, boundary conditions, various scenarios. So considering fastener tension allowable can be calculated by the following equation. PT allowable is equal to pi by 4, D effective. Now I've said rather than the D shank diameter, that's the nominal diameter is the shank diameter over here. But near the fastener thread, you can see there's some reduction of the area. And that's what we need to consider. Rather than considering the fastener diameter, we have to consider effective area over here. So D effective area into FTU. FTU is allowable tension for the fastener material. So now D effective, how do you calculate the D effective? There's a method which is given in this by R.T. Barrett, NASA Fastener Design course, and I sent last week this design, the report, which Prof. Dinesh has already downloaded, uploaded to the directory from where you can get this. So in threaded region of fastener, tension area is reduced, and thus effective diameter can be calculated as D effective equal to D nominal, which is a shank diameter, minus 0.9743 upon N. N is the threads per inch. D is the effective diameter, D nominal fastener diameter. Okay. In the absence of fastener data available, effective diameter can be approximated by 0.85 into D norm. The factor 0.85 is conservative for large diameter fasteners. Okay. So then fastener tension margin is calculated by PT allowable, which is from the previous equation, which I've said, upon P allowable minus 1. Simple. I've given some example. I picked up the data from for ILOC fastener. Dash 8 is a quarter inch, which is 6.35 dash 12 like that. These are fastener designation. Threads per inch, effective diameter D effective I calculated based on this equation. And as you can see, 0.86, 0.89 is a D effective upon D nominal. And as you remember, I said, okay, conservatively, if data is not available, as a conservative estimate, you can consider 85% of D nominal will be conservative, as you can see from this one. Okay, now, fastener single shear strength check. So now, instead of laminate, the fastener could fail in shear. So fastener shear strength allowable can be calculated. PS allowable is equal to pi D ref by 4 into Fs. Fs allowable shear strength of the material, fastener material, and again D effective, that is a nominal diameter. Okay, I've explained it over here. So again, MS pull allowable upon applied minus 1, simple. In case when you have shear and tension both, then you have to use the interaction. So now, in order to consider interaction, I've used some interaction equation. There are many different equations available depending upon scenario. So for the interaction, I've considered this method. So criteria even for bolts in joints with no gaps or shims, a single shear plane and threads and loaded and combined, shear and tension with joint is expected to separate before rupture. Following criteria can be applied. This I have taken from this report. I might have sent this also to Prof. Dinesh, I think. Otherwise, you can download always from NASA website. So this is the criteria. Normally, you will find in Brown the shear and tension criteria following a quadratic relationship. That is, shear square plus this square equal to 1. And which may be true in some cases it may not be true, and that is why it's good idea to consider the real criteria based on some test data, and this report shows the criteria and the test data and how they generated the criteria. So I think this could be useful for when you are doing some analysis of the structures. These fastener failures. Criteria 2, yeah, this is what I was saying. For bolts in joints that are not expected to separate prior to rupture, the following criteria can be used. That's quadratic equation. Conservatively, I have said apply criteria 1. That is this equation, which is conservative, because if you don't know, so this may be non-conservative sometimes, and this is better that way. My experience also has been that this equation sometimes is non-conservative for certain scenarios which we have studied. Okay, fastener joint pull-through scenarios. Pull-through can occur in such situations, you see. So, and failing a joint. Bolt bending case also will create the bolt pull-through. The shear when this at high load, the fastener tries to rotate, bending occurs, and it tries to pull in. So various cases, and that is why bolt pull-through has to be considered. Okay, so we consider the bolt failure under tension load, but however, another mode could occur if the bolt doesn't fail, but the laminate may fail. And quite often for thin laminate, it is the failure of the laminate which will occur before the bolt fails. So fastener tension load is created by laminate under the head as compressive stress is over here. Laminate between the whole boundary and the support experiences a shear force V and the bending moment M. I've just shown over here. So what happens? There's a moment, there's a shear, the compression underneath this fastener head, and all these modes may create different scenarios. I've shown some scenario over here. So when the load is applied, you have supported. This is like a ring. There's a fastener pull-through standard test from ASTM. So compressive stresses under fastener head through the thickness and interlaminar shear stresses. So here it will create the interlaminar shear stresses and radial cracks surrounded by circumferential stress. So you see what happens when you're pulling this, there's a bending. Circumferential stresses are created in bend due to bending. And you can see these cracks in the laminate. And when the cracks occur, the hole gets enlarged and the fastener can just pull through. So fastener doesn't fail, but laminate fails. I've seen in many cases the cracks like that in the test. The laminates crack. And fastener just pulls out rather than failure, fastener failure. But for a thick laminate, the fastener will not pull out. It may, fastener head may fail, or it may fail at collar. So here, prediction of pull-through load is difficult theoretically due to complex damage mechanism in the hull. So you have to determine this pull-through load from the test data. That's what I've said here. So MS pull-off load equal to P pull-off allowable and P applied -1. All these things I explained. Okay, now when we prepare the charts, there are various failure scenarios, as I said. There's a fastener can pull out through the laminate, or if the laminate is very thick, the fastener may fail at head or the collar. So generally what happens when we prepare the data allowable, we can write that allowable as a function of dt, diameter into thickness, and say for smaller loads, small thicknesses, it may be just a linear behavior. But for large thickness, what happens? The failure will not be dictated by the laminate, it will be dictated by the fastener. And that is where we say, okay, there's a cutoff, PT allowable, this is a fastener failure, and this is pull through. So sometimes if the laminate is very thick, you may just use this data allowable, thin somewhere here depending upon DT. Bolt bending failure, I'll be discussing in the following slides, of course. Here, this slide I showed last time for that normally the thickness to diameter ratios less than 0.8, and this one less than 1.6. Okay, now let's consider bolt bending failure. So I've just tried to discuss the scenario over here. You have single shear joint before bolt deformation, but as when you apply the load, then bolt may deform under shear loads. Okay, and when it deforms, what happens? Look into situation. This load is being pulled this way. This is applied this way. So fastener is in contact at this point and at this point. There's no contact over here. There's no contact over here. Similarly here, it will contact over here, it will contact over here. So that means rather than having the fastener making contact with the laminate throughout the thickness is not there. It partially makes a contact. That means it applies higher stresses over here, then high stress in this region. High stress over here, high stress over here. Sorry, there will be low stress over here, low stress over here, depending upon the equilibrium situation. But high stress is right over here and here, near the on the inner surface. So I just try to show over here what happens now. So the equilibrium will be, say, when the load is being applied on the fastener, this one, and here, this one. So in terms of reaction, there's a reaction over here, and also there's some tension load created because that's what will react the moment. One next slide I'll show where I've tried to show the equilibrium. So here, as I said, the stresses at this face, what you see here, this is a line. So this is in contact with this one. So the high stresses and the stress variation is this, bearing stress. Very high stress over here. And on this plane, this is in contact. So this is what happens. You're applying the load assuming the uniform load, but it doesn't happen uniform load. The high stresses occur at the interface between this laminate and this laminate in this region. And this is the fact we have to account for when we are writing the bolt bending equilibrium. So the equations are developed based on this approximation. So as a result of the bolt deformation, the effective shear force acting on the bolt can be assumed to be triangular and maximum bearing stress near the interface of the strap. Okay, the maximum. Bolt shear loads P1 are reacted by the moments M1 and M2. So now, due to this one, what happens? This has to be in equilibrium. And where the loads get rejected then? Suppose the collar and this is not there. Then what will happen? When you are applying the load, it will just fail because there's nothing to react this load. Now, so this load, you see, creates the bending moment, okay, on the fastener. This bending moment has to be reacted somewhere, and this reaction is mainly through this M1 and M2. Okay, so that means M1 and M2. Now what happens here, we consider some kind of averaging in this region. And we try to say, effectively, our thickness of reacting the load is not the laminate thickness, but somewhere lower than laminate thickness. So most of the stresses are being reacted over here, where laminate thickness is up to here. And that is where we are considering, okay, this is our effective thickness, and this is effective thickness. And so I've shown, okay, so within the effective thickness, we consider, okay, the constant stress in this region. Okay, so this is the effective thickness, and this is the effective thickness. And the moment arm then will be from here to here. So we write the equation FB maximum I, which is maximum stress, is equal to 2P1 upon D Ti by 2, which is 2 times the average bearing stress within half. So average bearing stress is P by dt. But we are considering, okay, it's a triangular distribution, so we consider double of that, which is 2 times the average bearing stress within half the laminate thickness. PRE considers the effective thickness at Ti by 2. Actually, effective thickness may be different to Ti by 2 and really calculated here. If you look in the PRE book, that is Aircraft Structures, 60 years ago, I think it was written sometimes in 1951 or so. So PRE considered this one, that effectively half of the thickness is reacting that, but one has to consider, using this equation, the equivalent thickness, effective thickness, rather than considering half thickness. So that's what I've done over here. As load P1 approaching the failure at ultimate, can be assumed that average bearing stress within the effective thickness TE1 and TE2 will occur as shown in previous figure and may be written as P1 equal to FBRG1, that is bearing allowable for a plate 1 and bearing allowable for plate 2. And these are effective thickness for plate 1 and plate 2. Okay, I won't go into the details of this is explained over here. So that means based on this equation, TE1, that is effective thickness equal to this one, and effective thickness TE2. All right, so I've defined over here, say this is my effective thickness now, and this is my effective thickness over here, and this is the shim thickness. So we'll write the equations now for general with the shim. So determination of bolt bending is based on the semi-empirical relation. B effective now. What is B effective? This is our B effective. That means moment when we are considering. So we consider the actual load is applied at the centroid of this one. But we said, okay, effectively what happens, this region is inactive. So stresses are considered within the effective thickness, and we consider, okay, within effective thickness, we consider the average stress. And if we consider the average stress, that means the loading arm will be at the center of this one to center of this one here. And that is why this is our B effective. So the moment on the bolt due to the applied load is this P1 into B effective. And then this moment has to be reacted by this moment M1 and M2. And this is what essentially is being done over here. Okay, so B effective is equal to TE1 by 2, TE2 by 2, plus K3. So TE1 we have derived previously, P1 upon D bearing, TE2 P1 upon D bearing, and K3 we consider 1. 1 is a conservative, depending upon the type of the shame, if it's a soft shame or hard shame. For hard shame, it may be lower than 1. But conservatively, we consider, okay, shim factor is 1. So based on that, and bolt reacting bending effective moment M effective can be written as M effective equal to M plus 1, M1 plus M2, which is equal to P1B effective. M1 is not equal to M2 generally, depending upon the collar and head type. It is difficult to determine the moment M1, M2, therefore an average moment is considered. M average, M by 2, this is. So FB max is this one, essentially. So once you have got this M average on the bolt, you can write down the maximum stress for the bolt for the give this moment. Okay, now IB, that is a moment of inertia for the bolt, simple equation. So FB max is this one. So bolt failure occurs when FB max is equal to allowable bending stress. Therefore, fastener bending stress margin is this. Simple. Okay, now I've just made some comments over here. Preceding slides have shown the determination of bolt bending moment and the bolt margin of safety. However, in addition to the bending stress, the bolt is subjected to the bolt tension, axial stress due to the PT, and shear stress due to the shear force. The tension load will behave as beam column on the bolt. The tension may slightly relieve the bending moment, is therefore not required to interact the tension and bending moment. So this is my comment, because when the tension is also there, bending is also there, it just try to relieve rather than increasing the. So however, effect of shear on a bolt may be interacted in to calculate the final margin. Bolt joint design guidance. So far, any questions on those methods? That basically the equations you can find in some references also, and read this presentation. If you have any questions, do ask me next time. Now, I'll just quickly run out with guidance. Most of the guidance I already talked about, but it is just summary, which I have taken from your handbook 17. So design the joint first and fill in the basic structure afterwards. Why we say that? Because it's better to consider joint design and then design other structure. Otherwise, when you have designed the structure, then joints are critical, they are failing, so you have to change a lot of dimensions. So the best thing to start with first, roughly design of the joint. Joint analysis should include the effect of shimming to the limits permitted by drawings. What it is saying, say, when the structure is being designed, you have suppose rib to skin joint. And as a designer, you will consider, okay, I can just consider rib thickness and skin thickness, and there's nothing in between that. However, in practice, when the manufacturing is done, sometimes the ribs to skin may not be fitting together easily. So they might have to put the shim. Shim degrades the joints, as I said. So now, at the design stage, when we are analyzing the structures, we have to assume that there will be shim, because that allowance for the shim has to be put on the drawing. And you have to calculate the margin, taking into account the shim. The shim could be 20 thou, say 0.5 millimeter. It could be 0.75 millimeter reliable. So minimum shim which you have considered in a design, effect of that has to be considered in static and fatigue margins. And the drawings will be showing that shim allowance. Whether shim is there or not, don't worry about it. But you are allowing the design to have the provision by the production for the shim. And the margins would be lower with the shim. But it's again necessary. Design joints to accommodate the next larger fastener size. So what we are trying to say, suppose you are designing the joint for 6.4 millimeter nominal diameter. Okay, we have written the margins, but it is possible during production something goes wrong. And they may have to increase the fastener size to next size. We call that 1/32 diameter. So right in the design stage, you would take into account that consideration to prepare the margins. Some oversized fasteners. Bolted joint strength varies far less with percentage of 0-degree plies in fiber pattern than does unnotched laminates. Okay, don't worry. Optimum single row joints have approximately 3/4 of the strength of optimum 4-row joints. What it is saying, do not keep on increasing the number of rows, because from the fastener load distribution I showed that usually is the first and last fastener will pick up the highest load and the middles won't pick up. So suppose your joints are having 3 rows, you increase to 4th row. That really doesn't affect significantly. You do not carry much load. So again, it's a question of optimization of the number of rows. Common errors in composite bolted joints are to use too few bolts, space them too far apart, and to use too small a diameter. Doesn't maximize the strength of the laminate. Rated shear strength of the fastener does not usually control the joint design. What it is saying, the shear strength, the fasteners will be shear strength rated, but it doesn't mean that much of shear stress you can apply on the joint, because that will be controlled by bearing, and bearing allowable will be lower. So bolt diameter is usually governed by the need not to exceed the allowable bearing stress in the laminate, not based on the shear strength allowable for the bolted bolt. The peak hook tensile stress around the bolt hole is roughly equal to the average bearing stress. Oh, this are already showed in that, so don't worry. Maximum torque values should be controlled, particularly with large diameter fasteners. What it is saying, that you have a large fastener and then torque values will be high or 100% torque. You have to really see whether by applying that much of torque, so that is converted the force, compressive force on the laminate, whether laminate will crush. Normally, the rating of the torques are given such that it will not cause the crushing of the laminate. Bolt bending is much more significant in composite than for metals, which I have highlighted earlier. The reason being, generally what happens, the bolt bending becomes critical because laminates thicknesses are generally larger than the metal. The reason being, say aluminum, bearing strength allowable for bearing is around 800 megapascal sag. Whereas for a laminate, after you have applied the knockdown factor for environment countersink, you may barely achieve more than about 7 into 7, around 500 megapascals. So there's a big difference in bearing stress allowable for the aluminum compared to the composite. And that is why you have to increase the thickness of the laminate in order to achieve the same type of load carrying capability in bearing compared to aluminum. That means strap becomes more thick. And if the strap becomes thicker, that means it's increasing the bolt bending moment. If bolt bending moment goes up, that means bolt will try to fail. And that is why bolt bending is more critical for the composite joints than the metals. Next one, optimum double wide ratio for multi-row bolted joints. I think it's almost going to be time. A couple of these ones, maybe I'll just take up next time about 10-15 minutes, wind it up. But before we close today, any questions?
Sir, just one doubt, sir.
Yeah.
Sir, aren't these bolted joints always used with washers or inserts sort of thing?
There will be always washers.
So in that case, correspondingly, our calculations also will change.
In the washers, in the sense, generally on the fitting side, there will be washers. But if you are having the ribs to skins, there may not be any washer, just the fastener and the collar. What happens? Actually, these collars have automatic, already got the washer. Normally nuts will have the washer separately, but collars, like high lock fasteners for the collars, they come with the washers automatically. So you don't use separate washers on that.
Sir, so basically that pull-out strength automatically increases, right, sir?
Well, this can pull out from the head side, not from washer side. But
okay,
only in case when the washer is there. But suppose you have the blind fasteners. A rib to skin on one side will be attached by the blind fastener, like a composite locks, say. So there's no washer over there. So it's not always the washer everywhere.
okay, sir.
If it is needed, then you would have the washer normally. Suppose you have the nut instead of the collar. You may have washer over there, but not necessarily always. Any other question?
Yes, sir. Radhaswamy here, sir.
Yeah.
Hello. Can you hear me, sir?
Yes, I'm hearing.
Yes. Sir, this is regarding the connecting of cables with bus bars in electrical system, where they will use a spring washer as well as a plain washer, both the washers.
Cable, electric cable.
Yeah, connecting to the bus, electric bus. It's a metal, actually. Bus is a metal.
Yeah, I'm not sure about the question actually.
Now, will there be more stress on the bolt if you connect with the spring washer and plain washer together, sir?
No, I'm not sure about it. That's I do not know
Yes, sir.
which one is a spring washer and which one is a plain washer. If you can send me the email,
Yes,
the
sir. Yes.
scenario,
Yeah,
I
I'll send it,
joined,
sir.
and then I could look into
Yeah. I'll send it with a
that.
picture example, sir.
Yeah. Now,
Thank
last week I sent one report on the Fasteners design guide.
Thank you, sir.
And in that report, you may find the use of fasteners and the collars and the washers really. Might try to go through that report. I think
Yes,
Professor
sir.
Dinesh has uploaded that
Yes, sir.
fastener design guide, and you can send me the email
Yes, sir.
about explaining the scenario which you have. I'll try to find an answer. I don't claim that I know about it,
Yes,
but
sir.
maybe I try to help you
Okay.
if I
Thank
can.
you, sir. Thank you, sir.
Any other
Thank you.
question? If there is no other question, okay, we can call it a day now.
Sure, Dr. Garg.
And so next Thursday, this Thursday,
Right.
I would spend about 10-15 minutes on this bolted joint. That will be over, and then I'll start the notch analysis, that is damage tolerance analysis.
Okay. Wonderful.
Okay, so good night.
Thank you. Good night. Bye-bye.
Bye.
Bye.
Thank you, sir. Thank you.